Ready? Hello again. In this lecture, we will speak about the use of nanomaterials in the fabrication of membranes. As you see in the next lectures, in most cases, we speak about the use of nanomaterials in the fabrication of membranes. And in most novel membranes, we say that the composite membrane and nanocomposite membrane can improve the resistance, stability, conductivity, flux, rejection, and other properties. Therefore, the use of the nanomaterials in the fabrication of membrane is very important, and the subject of my PhD thesis 15 years ago was the use of nanomaterials in the membrane fabrication. And in that time, the nanotechnology was very new subject. And when I began to my thesis, not famous, but the time showed that the nanomaterials is very important in modification and fabrication of the membranes. And today, we have commercial used our own membranes that use the nanomaterials in the fabrication of commercial, our own membranes, commercial UF membranes, and maybe some companies use the nanomaterials and do not say use because have published some patent, and they was not now in other companies their formulation. Therefore, in this lecture, I try to introduce different type of nanomaterials and their applications in the membrane fabrication. I published more than 200 papers about use of the nanomaterials in the membrane fabrication. We generally say that name these membranes as mixed matrix membranes. When we say mixed matrix, we mostly speak about this type, that we added the nanomaterials to the matrix of monomer or matrix of the polymer and fabricated the membranes. But when you use the nanocomposite materials or nano-enhanced membranes, this label, this name is very general and can cover all of the type of nano-used membranes. There are some other names such as hybrid inorganic organic membrane, nanocomposite membrane, composite enhanced membrane, and others. Generally, we have two types of the mixed matrix membrane, which is blended in phase inversion technique, and second is the TFC layer. We know that the active layer and the selective layer is the surface of membrane. Therefore, if we use the nanomaterials in the surface of the membranes, the efficiency will be increased. And as you see in the previous lecture in surface engineering, with atomic layer deposition, with chemical vapor deposition, physical deposition, and other surface engineering techniques, we coat the nanomaterials on the surface because the surface layer for separation is important. And other bottom layers is only act as a support. Therefore, we try to use low amount of nanomaterials because generally the price of nanomaterials is high. And if we use low amount from economical view, it's good. Aim of using nanomaterials in membrane, increasing permeability, increasing hydrophilicity, or increasing hydrophobicity. Based on the membrane, if we want to increase hydrophilicity, we must use hydrophilic nanomaterials. And if we want to increase hydrophobicity, we can use hydrophobic nanomaterials. Therefore, one of the important properties of nanomaterial that we can manage the functionality. If we use hydrophobic functional, our nanoparticle will be hydrophobic. We have antibacterial nanomaterials such as silver-based, zinc-based, graphene-based. They can destroy the cell membranes of the bacteria, microorganisms, and have anti-fouling properties. Therefore, with addition of these nanomaterials to membrane, we can induce antibacterial properties to the membrane body. Anti-fouling improvement, with addition of nanoparticles, we can reduce roughness, we can increase hydrophilicity, and others cause to the low fouling of the membrane. We can change the membrane surface charge with coating of the nanomaterials with high negativity or high positivity. We can change the membrane surface, or we can add photocatalytic activity to the membrane. With mixing or coating of photocatalysts on the membrane surface, we can have a photocatalytic membrane. Or we have a catalytic membrane. We can coat a catalyst that can cause change of one molecule to another molecule. And this membrane acts at the same time as separation layer and as catalyst layer, and other properties. First, I want to define what is nanomaterials. Okay? It is better we say nanomaterials. In most cases, we say nanoparticle. Nanoparticle is one of categories of the nanomaterials. The general name is nanomaterial. And this nanomaterial, as a simple definition, that we say at least one dimension should be less than 100 nanometers. One dimension. In nanosheets, for example, graphene. Graphene is a sheet with diameter of 5 micrometers, 5,000 nanometers, okay? Therefore, from length, the graphene is not nanomaterial. But the thickness of the nanosheets is important. In nanosheets, we say that the thickness is nanometric. The thickness of the graphene is about 10 nanometer. Therefore, the nanosheet graphene is a nanomaterial. Or in nanotubes is tall length, micron, but the diameter of this matter, these tubes, these fibers should be nanometric. Oh. Therefore, at least one dimension. If we have about 3 dimension is nanoscale, we say nanoparticle. Oh. Nanoparticle is a sphere. This is a nanoparticle because have a circular form, and in about 3 dimension is nano. Therefore, when we say nanoparticle, that means it is the nanosphere-like. But this nanosphere can have a different morphology. Okay? In most of the materials, such as metal organic framework, we say nanostructure, not say nanomaterial or nanoparticle. That means in most of the MOFs, the dimension is more than the 100 nanometer, okay? But there is some pores, some porosities in this micrometer particles that have a nanometric size, okay? In this case, we say nanostructure. If we have a material, if a particle that have nanometric pores and porosity in their body, we say nanostructure. Therefore, nanostructure have not nanometric size, okay? Most of MOFs, ZIFs, zeolites is the big size, micron. But they are angstromic and nanometric pores that, in this case, we say this is a nanostructure. We have a nanorod and different categories and configuration. The famous one is here. Also, we have a carbon dot. No? Carbon dots are quantum dots. Okay? When the size of the nanomaterials is less than 5 nanometer, we say quantum dot. Okay? Quantum dot is very, very small. And when very small, the properties of nanomaterial also change, and the properties can be influenced with the size. Have a different classification. We have a 0 dimension. That's the most one is carbon dots, clusters, hollow nanoparticle. As you see, all of these nanosphere, nanoparticle. Therefore, carbon dots is 0 dimensional, and that means very, very small. We have a nanorod and nanotubes that you see, nanowires or nanofibers. 1 dimension, the thickness, diameter is 1. 2-dimensional, you see this one. We have a nanolayer. When we nanolayer, nanocoating, when we have a RO membranes with a polyimide layer lower than 100, we can say that we coat a nano layer. Our nanostructures, mostly here, that they are categorized as a 3D material. One of the most and important properties of the nanomaterials is that we can chemically modify the nanoparticle surface for changing of the properties. In literature, you can find at least maybe 100 modification for carbon nanotube, for graphene. For graphene and carbon nanotube have carbon-based and can be prepared from graphite. And these carbons and have 2 bonds. These free electrons in the graphene, you see, we have these groups, okay? That means we have 2 electrons, and these electrons can be react with most of the compounds. We have a active area for reaction, and we can add different functional groups, amine groups, acid groups, sulfonic groups, hydroxyl groups, to the surface of the nanomaterials, carbon-based, and we change the charge. We change the configuration. We change the positively and negatively. We add here for Jupiter ion and cause to the antibacterial and others. Therefore, we can change the most of nanoparticles with chemical modification and produce different categories of the nanomaterials for different applications. Or we can mix two nanoparticles together, 3 nanoparticles. In this figure, you see nanotube coated with a nanoparticle, with a magnetic nanoparticle, and these magnetic properties can be used for increasing hydrophilicity. For example, this hematite is hydrophilic, can increase the electrical conductivity, and other applications. Therefore, the nanomaterials can be easily modified, can be easily coupled with other nanoparticles, and can be hybrid with other polymers. For example, we can coat the surface of the nanomaterials with a polymer, or we can graft some monomers on the surface of the nanoparticles. As I say, from this year, the nanotechnology have growth and have a new progress. And you see that in years, 2010 years, began to rapid publication about the nanomaterials. But the first use of the nanomaterials can be gone to these years that speak about the nanopores, about the size of the membranes. But in 2010, we have the best progress in the nanotechnology. And first, you see the carbon nanotube, and carbon-based is mostly used, and next, novel nanomaterials is synthesized, and every day, new type of the nanomaterials is synthesized and introduced. For example, we now max phase or maxsense. Maxsense is similar to the graphene, but fabricated from inorganic materials. Instead of carbon, in the graphene, we have a titanium, aluminum, and other metals that have a very high resistance to temperature, and we can use instead of graphene in many places. Almost in all of the membrane processes, nanomaterials have been used for liquid separation, for gas separation. All of kind of the nanomaterials have been used, all of kind. And in all fabrication methods, we can use the nanomaterials. And one of the most used is that we can easily use. In the most cases, we add the nanomaterials to the solvent and use ultrasonic for good dispersion. And after that, we add monomer, we add polymer, and other process. Therefore, the use of nanomaterials only needs a good dispersion and no add a new equipment, a new instrument for the membrane fabrication, and therefore can be used easily in the membrane fabrication. In this slide shows the different type of the nanomaterials have been used in the membrane fabrication. For using of a nanomaterials in membrane fabrication, three properties is very important. One, high dispersibility. The nanoparticles, nanomaterials should good dispersion. What is dispersion? When we have a dry nanomaterial, they are collected together and attached together. When we add these nanoparticles to the solution, organic or water, they do not tend to separation from together. Okay, we must separate them from together and disperse uniformly in the solution. For this one, we can use the high rate mixing, and when we high rate, the nanoparticles contact together and can separate together. But the easy method using of the ultrasonic, that the produced bubbles can knock to the particles and cause to the dispersion. This dispersibility is an interaction between nanoparticle and solvent. Some nanoparticles have good dispersibility in organic phase. Some have good dispersibility to aqueous phase. Okay? Hydrophilic nanoparticles could disperse in water. Hydrophobic nanoparticles could disperse in organic solvent. Therefore, for increasing of dispersibility, we can, in some cases, change the properties and surface of the nanomaterials. In fabrication of polymeric membranes, we most use organic solvents, dimethyl acetamide, dimethyl formamide. In this case, when we add the hydrophilic nanomaterials, the nanomaterials have not good dispersion. In this case, it is better we use carbon-based nanomaterials. Carbon-based nanomaterials good disperse in organic solvent, because organic solvent is carbon-based. But when we have a water in RO preparation, or we can add the nanoparticles to the coagulation bath, to the non-solvent bath. In this case, it is better we use inorganic nanoparticles, such as metal oxides. Metal oxides is good dispersed in water. The second problem is the compatibility with polymer. Some nanoparticles have not good compatibility and agglomerate or aggregate. Agglomeration, that means when we add the nanoparticles to the polymer solution, no good compatibility between polymer and nanoparticle. Therefore, nanoparticles reconnect together and prepare a big particles. And these big particles cause defect in the membrane and reduce the rejection, or block the pores and reduce the flux. This compatibility and dispersibility in most cases related to the nanoparticle concentration. Most of nanoparticles, nanomaterials, have good dispersibility in low concentration. When we use 1%, have good dispersibility. But when we increase to 3 or 5%, very bad dispersibility, very bad compatibility, and with addition of more concentration of the nanomaterials, the properties of the membranes reduce. the flux reduced, the rejection reduced. Therefore, the low amount, in the most cases, low amount of the nanoparticles is good for membrane fabrication when we mix the nanoparticle, not surface coating. In the surface coating, no problem. But when we mix the nanomaterials in solvent, in polymer, as a mixed matrix, in this case, we must use the low amounts. Higher amount is not good. And the nanoparticle should have high hydrophilicity or high hydrophobicity for increasing. Some nanoparticles have very low functional group. And because we have a use low amounts, 1% to 2%, the low functional group is not good. It is better we use the high functional groups, such as dendrimers, for fabrication of membranes. Almost all of the nanomaterial have been used in the modification and fabrication of membranes, multi-wall carbon nanotubes, single wall, carbon dots, nanodiamond, boron nitride, hematen, bioten, maxen, molybdenum sulfide, graphene, carbon nitride, and most cases, zeolites, different kinds of zeolites, different kinds of clays, most of the metal oxides. For example, this nanomaterial, as these nanomaterials have a antibacterial properties. You can see we can couple the two nanomaterials with together. Or three nanomaterials can be coupled together for increasing the properties of the nanomaterials. For fabrication of mixed matrix membranes, there are different techniques. The first technique that used 20 years ago for the first time when introduced is the self-assembling or deposition of the nanoparticle on the membrane surface. After fabrication of the membrane, this is a commercial membrane or we prepare beforely. After fabrication, we produce a suspension of the nanoparticles in solvent with sonication, and the prepared membranes immerse deep in this nanoparticle solution and keep for 1 hour. And in this case, nanoparticles deposit and self-assemble on the membrane surface. And the membrane surface is important because the separation layer is the top surface. In this case, we have a high efficiency and the contact angle reduce rapidly. Okay? But nanoparticles are not stable because physically attached, and when we use the membranes with cross-flow fluids, this cross-flow tension can be separate the nanoparticles, and after 1 day, we have not nanoparticles. Therefore, this is efficiency because located on the membrane surface, but the attachment is problematic. For increasing the attachment, now we use the atomic layer deposition, magneton sputtering. In this case, the growth of, in this case, we have a ready nanoparticle in this. Ready, and we only deposit the nanoparticles on the membrane surface. But in the plasma, atomic layer, magnetic, and as discussed in the lecture, the previous lecture, the nanomaterials self-grows on the membrane surface and the pores and the top pores, okay? And in this case, we have a good attachment between the nanomaterials and the polymeric. When we have a growth, not deposit, growth of the nanomaterials, the attachment is very good and we have a stable layer. But this method is very easy, but in the atomic layer deposition and other sputtering technique, we need very expensive device. This is an example of this method that showed that coat the graphene oxide ion nanoparticles on the surface of RO membranes. The second method that's similar to the one, use of the filtration. In this scale, the nanoparticles self-assemble and not good stable. But in the second method, we use the filtration and pressure. When we use the pressure for coating of the nanomaterials on the membrane surface, we have a better stability. And in some cases for carbon-based, for carbon nanotube, for graphene, the membrane is stable, have a good stability. But after 10 days, 20 days, this membrane types is also detached. Because this technique is also physically and not good attachment. But it is better than top one because we have a use pressure for coating of the layer. These membranes mostly named as Bucky paper membranes. When we have a polymeric support or ceramic support and coat the nanomaterials with pressure on the membrane surface, say that we prepared Bucky paper. For increasing of the stability of the nanomaterials, after the coating of the nanomaterials by self-assembling or by filtration, we can use an adhesive. We can use an polymeric layer that protect the nanomaterials from the attachment. Usually chitosan, PVA, polyacrylic acid used as a dishydrophilic layer. But the coating of this layer increase the thickness of the membrane, reduce the membrane flux, and coat the surface of the nanoparticles. In this case, the top layer will be the coated polymer. And the efficiency of nanomaterials reduce because we have an extra layer. But the stability is good, and the coating of PMMA, PAAA polymers can increase their stability. For reduce the effect of this coating properties of the hydrophilic polymer, it is better we disperse the nanoparticles in this hydrophilic polymer and the next coating on the support. In this case, the possibility of the location of nanoparticles on the membrane surface increases. It is better we mix the nanoparticles in the monomer or polymer solution and next coat the membrane surface. This is an example of this one. But the simple method and the most used method is blending technique or embedding technique. We say blending or embedding technique. Embedding technique. In this method, we first select the solvent. Solvent should dissolve the polymer, okay? And we first add the nanoparticulates or nanomaterials to the solvent and use good dispersion. And after preparation of a good dispersed suspension, we add the polymers, okay? For stability of the nanomaterials and reduce the agglomeration, we can use surfactant. Surfactant causes to the good dispersion of the nanomaterials, or we can add some hydrophilic polymers. When we add a polyethylene glycol, a PVP, and polyacrylic acid, these hydrophilic polymers attach to the surface of the nanoparticles and do not allow to agglomeration, to aggregation. Therefore, in some cases, here we add surfactant, or after good dispersion, we add a polymer, another polymer with low amount, 1%. The polymer concentration is 15 or 20. We add 1% polymer for reducing the agglomeration possibility. This extra polymer can be also pore-former. We use pore-former in membrane fabrication for increasing of porosity. Therefore, in most cases, PVP can act as both pore-former and good dispersing agent. And after preparation of the good solution and degassing, we cast the membranes and prepare the mixed matrix membranes. If the non-solvent is water, non-solvent mostly is water, and the nanoparticle is hydrophilic, during the phase inversion in coagulation bath, we have migration of nanoparticles to the surface. Migration. When the water, where we put the film in the water, the solvent exit and the water won't go to the membrane body. In this case, because the hydrophilic nanoparticles want to go to the water phase, some of them migrate to surface. And we see by EDAX analysis, EDAX analysis is coupled with SCM. And in this case, for example, our nanoparticle is titanium dioxide. We say to SCM operator, give the titan EDAX. And for example, when we have this membrane, show that the density of the titanium in the top layer is higher than bottom layer. And this shows that the most of titanium layer migrate to the surface, and we know that the surface layer is important. Therefore, in this technique, we have migration of the nanoparticle to the surface, As I said that it is better we can. Okay. Yes, properties. The active layer of the membrane is top. Okay. When nanoparticle migrate to the top layer, it is better for us because we added the nanoparticles for improving flux, hydrophilicity, charge, and when located on the top surface, it is better. Your question is this? Huh? I truly understand your question.
My question is, if the nanoparticle migrate to the surface, if the nanoparticles have hydrophilic nature,
Yes.
and again the solvent, non-solvent is water,
Okay. Yes.
which is hydrophilic, it doesn't affect the membrane property.
Yeah, affect in the membrane property. Yes.
So why we choose
Why we used which?
So we have to coat membrane with another layer, polymer layer, and just prevent the movement of nanoparticle to surface water.
Yes.
So in that case, membrane become better.
Yes, better. If I understand your question, we want to locate the nanoparticles on the surface. But in the surface, the nanoparticle can be leached and not stable, as presented in the previous methods. Okay? In this method, we say that the nanoparticles on the surface is not stable. Therefore, but when we mixed with the matrix of polymers, because of the interaction between the polymer and the nanoparticle, and also trapping of some nanoparticles between the chain of polymers, the stability increases. Okay? We must have uniform dispersion, but we see that we have a migrate to the top layer, and it is good for us because the selective layer is top layer, and the bottom layer is not very important, only for increase of stability. Therefore, this migration is good for us.
Sir, then what will happen to the strength of the membrane?
Repeat.
Strength of the membrane.
Yeah.
Does it affect the strength of
Yes. Some of the problems, I speak about the problems. In some cases, the strength of the membrane increases with addition of low amount of nanoparticles. In industry, we have a composite polymers that add some clay, some zeolite, some fiber chop to the polymer, and this addition of the material increase the strength of the polymers and used in the airplane fabrication. In this case, when we have a low amount of nanoparticles, the strength increase 10%, 15%. But higher concentration, 5 and more than 5, reduce the flexibility and strength of the membrane. Okay? And also agglomeration of nanoparticles reduce the strength. When we have agglomeration, we have a defect, and the agglomerated place is suitable for broken. Okay? Therefore, it's good for us. There are many methods for growth of the nanolayer on the membrane surface, as speak about ALD, magnetron plasma. One method is the contra-diffusion method. Contra-diffusion or counter-diffusion. Contra-diffusion, we have a similar setup in lab that we first select a porous membrane. We prepared it before this membrane by phase inversion, or this is a commercial membrane. Put in the cell between two phases, between two solutions. We have one solution in the top of membrane, and we have another solution in the bottom of the membrane. And we have this U tube, or instead of U tube, we can use a pump. Why we use U tube? Because we have a very low pressure for drive the bottom solution to the top layer. Okay? In the one solution, we have a first agent, and in the top solution, we have a second agent. The first and second agent can react together and prepare a nanoparticle, nanomaterial. For example, in this paper, ZIF-8 was grown on the PVDF support. For fabrication of the ZIF, we need the zinc ions and 2-methyl-imidazole ligand. With reaction of the zinc with 2-methyl-imidazole, the ZIF layer was grown on the membrane surface, and if possible, in these layers, top layers, pores, and relatively we have a good attachment, and we say this membranes is inorganic organic membranes, or inorganic coated polymeric membranes. We have also have polymeric coated ceramic membranes. In this case, we have a ceramic coated polymeric membranes. And the active layer will be this grown ZIF-8 layer. And generally, the inorganic materials have very good anti-fouling properties comparing to the carbon-based polymers, because most of the fouling agent, oil, proteins, fat, are carbon-based, and polymer is carbon-based, therefore easily attached together. But when we have inorganic ceramic materials, the attachment is low. Therefore, ceramic membranes have lower fouling than organic polymers. This method is one method for growth of the polymeric layer. As discussed in the previous lecture, we can use the nanomaterials as interface layer in the fabrication of TFC membrane. That use of these nanomaterials reduce the intrusion and increase stability and cause to the thin layer on the membrane surface. For increasing the stability of the membrane, the nanoparticles on the membrane surface, we can chemically connect the nanomaterial to the membrane surface. In this, our discussed methods, we have a physically mixing, physically coating. But we can produce carbon-carbon bond between polymer and between nanomaterials. That's called the grafting. Grafting is a chemical bonding. In the grafting, for example, we can graft this dendrimer to a graphene oxide, and then this group can connect to the membrane surface. Therefore, we have a chemical reaction. We can modify the nanomaterial surface for connection to the membrane surface layer. This is very, very stable because chemically connection very stable. For example, in this paper, these nanomaterials grafted to the membrane surface and increase the fouling resistance of the membrane. In the TFC membranes, we say that we have a very thin layer on the support layer. In this case, the use of two-dimensional nanomaterials in most cases cause to the increase in roughness. Increase in roughness. And increase in roughness is not good for membranes from fouling view. Therefore, it is better we use very small nanoparticles in modification of RO membranes. For example, in this study, use the coupling of titanium dioxide and carbon dot. If you see the literature, you will see that one inorganic nanoparticle coupled with carbon-based nanomaterials. The reason is that the carbon-based nanomaterials, such as graphene, carbon nanotube, have a good dispersion in organic solvent. But inorganic materials have a high functionality, high hydrophilicity. Therefore, with coupling of one inorganic with organic nanomaterials, we have both good functionality and good dispersion. Therefore, many papers coupled one organic and one inorganic materials. And in this paper, we see with addition of the nanomaterials with very low amount, the flux relatively 50% increased. With very low amount, we can increase 50% in flux of the membranes. And you see, this is no nanoparticle and have rough surface, but with addition of nanoparticles, the roughness decrease, and the decrease in roughness can cause the membrane antifouling properties. Without nanoparticles, after 12 hours, the flux relatively 35% reduced, but with addition of nanoparticle, only 5% reduced after 12 hours. This shows that very low amount increase the flux and reduce the fouling. Also, nanomaterials can be used to increase chlorine resistance. In TFC membranes, in polyimide TFC, I said that the chlorine can destroy the polyimide layer. With addition of some nanomaterials as a trap, the chlorine resistance can react with nanomaterials and do not react with polyimide. Therefore, chlorine resistance increases. As showed in this reaction, this schematic, with addition of the, for example, ICP nanoparticle, the chlorine resistance increased. You see here, after chlorination, the NaCl rejection reduced from, for example, 98 to 8. But with addition of this nanoparticle, no any change in the rejection that shows the membrane have a good resistance. Also example of that. The nanomaterials have been used in commercial RO membranes. For the first time, nano H2O RO membranes is used, probably zeolite, in the fabrication of the commercial membranes. I speak about the advantages of our nanomaterial-based membranes, but we have some challenges in the use of these nanomaterials. As I said, in most nanoparticles, we have a poor dispersion, and agglomeration is a problem, and the cause to the reducing strength of the membrane, reducing the flux. And in this schematic, we show the agglomeration. In some case, cause to the crack. And the most problem is leaching. We want to use the the membranes for 3 years, 4 years, and most of nanomaterials can be leached or released from the membrane body during the time, and after 1 year, maybe we have no nanoparticles in the matrix of the membrane. Therefore, the chemical graft is better method for no leaching, or we can increase the interaction between polymer and nanomaterials for reducing of the leaching. There are some environmental problems and healthy problems in some nanomaterials, and this leaching to the water may be some environmental problems. Some of nanomaterials can be toxic and we cannot use. Most of nanomaterials prepared from heavy metals, zinc, nickel, cobalt, and they can be toxic, and another. There are some suggestions for reducing of these challenges. For example, for reducing of the agglomeration, we can modify the membrane surface. We can use surfactant and others. For reducing of the leaching, the two-dimensional nanomaterials have low leaching. When we have a very small nanoparticles, the leaching probability increases. But when we use the two-dimensional or nanosheet membranes, nanomaterials can be trapped between the polymer chains, and the release is very, very low. For metal oxide, release is high. For two-dimensional is low. Also, I say that in all processes, all fabrication methods, phase inversion, electro-spun, hollow fiber, TFC, interfacial, all processes we can use nanomaterials, and for example, in this slide, used in the electro-spun one, or coated nanoparticle on the surface of the cellulose acetate support as a bulky paper. And generally, as this slide, after 15 years research in the nanomaterial used in the membrane fabrication, I think in the recent future years, we will see that most of commercial membranes will be used the nanomaterials in the fabrication of membranes. Thank you. If you have any questions.
The one that you mentioned earlier.
Yes.
Can we specifically deposit or decide the precise locations by using an atomic force microscope? Like I meant to say is this, that the sputtering technology that we are actually using it, my first thought comes in a mind is about the uniformity that we are going to have of a nanoparticles on the surface of the membrane. So the previous methods that you have mentioned earlier, which one is the probable with the high success rate to have the uniform rate of an nanoparticles to be deposited? Like the CVD that you have mentioned, you have mentioned the atomic force microscopy that you have mentioned, and there are few more were there.
The uniform coating of nanoparticle is very important. For example, in a filtration method, when we filter the nanoparticles from the membrane, if the pore size of the membrane is different, one pore is big, one pore is small. Therefore, most of the solution will go from big pore, and the most nanoparticle will coat on the big pore surface, okay? And we will have not uniform. Or in this method, contra diffusion method, if we have a not uniform pore size, we will have not uniform growth, because when we have a big pore, this pressure causes the more diffusion of zinc from big pore. Therefore, we will have challenges in this case. But the high technologies, such as atomic layer deposition, magnetron growth, have a very, very unique form. And why I speak about the magnetron sputtering? We have a different type of sputtering. In the magnetron sputtering, because we have a magnetic field and both electrical field, this magnetic film causes the very, very uniform deposition or growing of the nanomaterials in the membrane. So, yes, the uniform dispersion is very important. And when we have one thick and one small layer, close to the brittle of the membrane, and it is not good.
And in case of a chemical vapor deposition, since it's
chemical vapor deposition, okay.
In case it's an inert process that is going to takes place. I mean to say is
okay.
The environment in case of an CVD will be the very controlled one.
Yes.
In which the inert gases would be probably there to actually help to deposit.
Yes. In CVD, chemical vapor deposition, we have a flow of gas, and the flow of gas, we have two monomers or two regions can go from the gas, and in the surface of the support, these two react and prepare a thin layer. In the CVD, because both gases come together, in some cases we have a non-uniform coating, because all of the regions come together, and in the first space we have a high reaction rate because high concentration, and when go from the surface, because of the reaction, the concentration is reduced. But in atomic layer deposition, we have a gas with monomer 1 come to the membrane surface, adsorb, and we have a vacuum, the second reagent come. React together as a one cycle. We have a vacuum, again, the first reagent come, second come. Step to step, cycle to cycle come, and in this case, we have a very, very uniform layer.
So can we say that the atomic layer deposition would be the best one among these methods?
Yes. Now for surface engineering, the best method is atomic layer deposition.
Thank you, sir.
Another question?
Thank you so much, sir. We are very honored for this wonderful presentation here. So next, what we will do is that we will proceed for lunch next. So the lunch timing will be 1:30 to 2:30. So after that, let us assemble.